So what we have in this first one is we have two 15-kilogram masses that are connected by a frictionless pulley. We have a rope then that's going to be connecting those. And when we let the system go, this hanging mass is going to fall down, and it's going to pull then the mass on the incline upwards up the incline. Now our setup for this is going to be exactly the same as when we have just two masses on a pulley. The one on the incline will have just one different term in there, but keep in mind how we've done those ones with just the regular pulley systems. And we'll follow the same procedure with this. So for those ones I remember, we took then just the free body diagram for each of the masses. Now because the tension has to be the same for each, we can make those tensions equal to each other, and because the accelerations are the same, then we can then use those tensions to solve for acceleration. So let's start with the hanging mass. If I look at this mass that's hanging down, I have a force of gravity pointing down, and now because it's moving downwards, that has to be my larger force. I'll have a tension force that's pulling up, and the net force then, because it's moving down, is going to be downwards. So we can do our net force equation there. So this is for the hanging mass. Now with your net force equation, your force net and your force of gravity have to be in the same direction. So I can do force net equals force of gravity, and then your tension, because it's opposite in direction, has to be minus. My force net is m times a. It's a 15-kilogram mass, so I can have 15 times a. The Fg is just mg, so it's going to be 15g, and then minus my tension force. I'm going to isolate tension, so move tension to the other side, and then I'll subtract the 15a to the other side. So I'll get 15g minus 15a, and then isolating my tension. And typically for these ones, we'll isolate tension in both equations. It's the easiest one to isolate, and then we can relate the tensions together and solve for the acceleration. And so this is exactly the same as the one for the hanging masses there, and the equation's the same as well. Now the one on the incline, that one will be a little bit different, but we'll follow the same procedure. So I have a tension force then that's pulling up. Now for this one here, the tension force, now this tension force should be actually the same as this one because they have the same length. So this is a bit long, but that's all right. So that's your tension force heading up. Now this is being counteracted by a force parallel. Now this one's frictionless, so we don't have a friction force, but if there was friction, you could just add an extra friction term there as well. But right now we have just the force parallel pulling down the ramp and tension pulling up the ramp. My force net then, because this is being pulled up the ramp, is going to be going in the upwards direction there. And so then for the mass on the incline, what we have then is my force net equaling tension, and those are going to be in the same direction, and then minus my force parallel. And then as before, we can put our variables in. This is also a 15-kilogram mass, but you follow the same procedure even if they weren't the same. So my force net is going to be m times a, so I'm going to have 15 times a. My tension force, I don't know, but it's the same as the one over here, so we'll end up relating those. Now my force parallel, remember, is mg sine theta, and so my mass is 15 times g, and then we have sine of, and it's always that base angle of 35. I'll isolate tension again, and I get 15a plus 15g times sine 35. And that equals then my tension force. So now I have two equations isolated for tension. I just need to make those two equations equivalent. And so tension for the hanging mass has to equal then the tension on the mass on the incline. And so we get then 15g minus 15 times a, and that equals then 15a plus 15g sine 35. I'm trying to solve for a in this case here. I'll bring all of my a's to one side, so I can add the 15a to the other side. So that's going to give me 15a plus 15a, or you could jump, of course, straight to 30a. And I'll subtract the 15g sine 35 to the other side, and so 15g and then minus 15g sine 35. I'm going to have 30a on this side, and so that's just 15a plus 15a. And then this one here, I could come up with a number right away, but I'll just carry that through for a moment here. With the 15g and then the 15g minus, or so 15g minus 15g sine 35. I'll divide out the 30 on both sides, and then I'll have an expression then just for my acceleration. And so we can put those values into your calculator, and we'll get 2.09 meters per second squared for the acceleration. Okay, so this is going to be exactly the same. We'll find that we end up just adding the two masses on the side with the acceleration, and then we take the difference then of those opposing forces. Normally this would be just the two masses there, or two gravitational forces, but here we've then just taken one of the gravitational forces and replaced it then with a force parallel. Once we know the acceleration, we can find the tension. Now we can use either of these two equations to find tension. I'm going to use this one just because it's a little bit shorter, but you could check and see that they work in both of them. And so my tension is going to be 15g minus 15 times that acceleration. And so I have 15 times the 9.81 minus 15 times the 2.09. And so then I get an overall tension, and again it will be the same on both sides, of 116 newtons. So in this next one, we have, again, a connected system here. So in this one, nothing's going to be hanging down like we have with our typical pulley systems. But both of them then are going to be going along surfaces. And so we have friction on both of them. It's the same coefficient of friction for both surfaces. But our procedure is going to be the same regardless of how these ones are set up. We're going to do net force diagrams on each of those, solve for tension. We can use the tension to find the acceleration, and then use that acceleration to find then the tension. So first of all, this one here, the one on the inclined plane, is going to be pulling this one down. So the 500 gram mass is going to be going down the ramp, and the 200 one then is going to be sliding along here. So let's start with the 200 gram box. This one's going to have then the tension force pulling it in this direction here. And then there'll be a force of friction pulling that one back. And then the net force we know is going to be going in the same direction then as that tension force. And so for my 200 gram box, now I will put that into kilograms there, but for the 200 kilogram box, I have my force net, which is going to be equal to the tension, and those two have to have the same sign because they're in the same direction, and I'll subtract from that my force of friction. So this will be 0.2 times the acceleration equals tension, and then minus, now my force of friction, remember, is mu times force normal. And because it's on a flat surface, that's mu mg then for those. So I get 0.2 times the acceleration equals tension minus mu, which is the 0.3 times the mass, 0.2, and then times g. And so we can isolate our tension. And so our tension will be 0.2 times A. Now 0.3 times 0.2 is 0.06. And so we get plus 0.06 and then times g. And that'll be my tension equation for the 200 gram mass. The 500 gram mass is going to have a slightly longer net force equation because we're on the incline here. So what's pulling this one down the ramp then is going to be that force parallel. And there's going to be two things counteracting that. I'm going to have a force friction heading up the ramp, and then I'm also going to have a tension force then pulling back up the ramp. And that's, again, just force of friction is always opposite the direction of motion, and the force of gravity is sliding down. Force parallel is always down the ramp, and then in this case, of course, my tension is opposing then the motion there. So when I do my net force equation, and my net force for this one, because it's sliding down the ramp, my net force then needs to be down the ramp. And so I get force net equals force parallel, and those two are in the same direction, but minus force of friction, and then minus that tension force. So here I get 0.5 times my acceleration. Now my force parallel, remember, is mg sine theta. So I get 0.5 times g times sine of 35. I can subtract my friction force. Now this is going to be mu times Fn. But remember, on the ramp, your Fn is mg cosine theta. So I'll have that term over there. Now I'll just take this negative tension. I'll move that to the other side. And then I can take this negative, or 0.5a, and move that to the other side as well. So I have 0.5 times g times sine of 35. This mu Fn is going to be then 0.3 for my mu value, the coefficient of friction. And then force normal is mg cos theta. And so my m is 0.5. I have g, and then I have cosine now of the 35. And then the last term, of course, is that minus 0.5a. Now, I can take this whole section over here and just replace that with a numerical value. And that would be probably a little bit of a quicker way of going about this. And so I'll just calculate that out, the 0.5 g sine 35 minus the 0.3 times the mass g cos theta. And so when I calculate that out, I'm going to get 1.6008, or 1.608, and then some numbers beyond there, and then minus then the 0.5 times a. And that'll just be a slightly shorter expression then to carry through my equation. Now I have my two tensions here. I know that those two tensions are equal to each other, so I get tension equals tension. And that'll give me then 0.2a plus 0.06g. And that has to be equal then to 1.608 and then minus 0.5a. I can move my a's to the same side of the equation, so I get 0.2a plus 0.5a. And so it's just adding this term to both sides. And I get 1.608, and then all the decimal places with that, and then minus this term here. So just subtracting that from both sides. And then times g. So here I'll get 0.7 times a. When I subtract these two terms here, I'm going to get 1.019. And I can divide out then the 0.7 on both sides. And when I do that, I'll get an a value then of 1.46 meters per second squared. My last step then is just solving for the tension. And so once I know a, I can just use this to solve tension. Now you could use either equation, but this one's probably just a little bit shorter. And then so I have 0.2 times the acceleration of the 1.46, and then plus the 0.06 times g. And so when I put those values in, I get a tension of 0.880 newtons. I need to add in the 0 to get my 3 significant digits. So the last section that we're going to be looking at is projectile motion questions again. But what we're going to be looking at is cases where the launching point over here is going to be different from the landing point. Now it could be higher than the landing point or lower, so it can go in either direction there. But if those two are different, we have to just kind of lose a couple of the assumptions we made for the other ones. And the biggest one is that trip up and trip down are going to be the same. Now if we restrict our point from the launching point to an equal height, for this region of the graph, trip up and trip down is the same. I can also say that my velocity vector here will be equal and opposite to the velocity vector here, but that's only for this region of the motion. If I'm looking at this bottom region over here, because I have this extra piece here, there's more time spent falling in this case than there is going up, and the speed here and the final speed down here aren't going to be equal and opposite because this one's been falling quite a bit. So as long as the launch and the landing point are the same, we have a couple of assumptions, like trip up equals trip down, and then the initial and final velocities are equal and opposite. Now those don't still apply with these ones here. The rest of the problem though is going to be the same. We're going to just do the two components, the horizontal and the vertical one, and solve for what we can in each of those components. Be really careful with your signs on these ones. That's probably the easiest place to make mistakes as we're going through these. So let's just run through this. The cannon is sitting on the edge of an 85-meter cliff. So I have an 85-meter cliff here, and so that's going to be my vertical height that it goes. We're launching at 120 meters per second. That's along then that vector, and so we're going to have to break that up, of course, into components. The angle here is 25 degrees. And so the first thing that we're going to look at then, and we'll just kind of run these through one by one, is what's the maximum height. Now to get the maximum height, we're going to be dealing with the y component. And it is still going to be true that at this highest point, the velocity value in the y component is going to be equal to 0. And so it's always going to be true for these, reaches the highest point, and then starts coming back down. And so if I look at just the y component for this particular one, I can put in then my final velocity is going to be 0. My initial velocity, now the initial velocity, remember, we can always get from the triangle, and so it'll be the hypotenuse of this, and then times the sine of the angle to get the height. And so we're looking for those two vectors. There's the horizontal component and the vertical component. The vertical one is always by the sine of the angle. So we'll take the 120 meters per second and then times sine of that 25 degree angle. Now that's being launched upwards. I'll take up to be my positive direction here, and so it'll be positive 120 sine 25, and that's going to make then the acceleration equal to negative 9.81 meters per second squared. And so what I can find then from here is just what is my displacement. And so that'll give me then from where I started to where I finished, and so I can use the VF squared equation then to solve that. And so I have VF squared equals VI squared plus 2A and D. My VF is 0. And you'll see the equations are very similar to what we did before, so there's not too much that changes here. So I'm going to get 120 sine 25 all squared plus 2 times negative 9.81, and then times my d value. And watch your negative sign here because we are solving for a direction, so we want to be just really careful with our displacement, so we want to be careful with our signs always. I'll subtract this 120 sine 25, so minus 120 sine 25 all squared equals 2 times negative 9.81, and then times d, and I'll just divide out the 2 times negative 9.81 on both sides, and that'll isolate my d value. Okay, you could solve some of those in intermediate steps there as well, but I'll just hold those all through. My distance here then is going to be 131 meters. Now remember, that's positive, and so it's heading upwards from my starting point, and so we are expecting then a positive value for that because it's in the positive direction. Now do watch carefully for what it's relative to. We can measure the height relative to our starting point, or in this case the bottom of the cliff, so make sure you're reading carefully. This one here we're looking for relative to the bottom of the cliff, so what we found is this value over here from our starting point to where we finished. But what we're looking for then is then this whole value, so I'm going to have to add the 85. Now clearly this isn't drawn to scale, but my displacement from the bottom will just be the sum of those two. So it's an easy calculation to do, but just make sure that you're watching out for that. And so 216 meters is going to be then my net displacement, of course, from the bottom of the cliff. Now part B then is looking at the total time that the cannonball is in the air. Now this is another case where people very often will basically break this up into a couple pieces. So they'll figure out how much time to get to the top, and then from the top all the way to the bottom. And you can certainly do that. But if you remember that these are all vector quantities, we can actually do this just all in one step. And so what we'll do is we'll do just another variable listing for my y component. And again, the time that it's spent in the air in this case is going to be the y component. And I know that because I don't know time or horizontal displacement, so I just don't have enough information then in the horizontal plane to solve for anything there. So I'm just going to do my variable listing here. So my first one, my VI, is going to be the same as it was before. So positive 120 sine 25. My acceleration, of course, is still negative 9.81. That'll be meters per second squared. And then what I'm going to do is I'm going to put in a displacement here. Now my displacement, and remember it's a vector quantity, I started up here and I ended down here. So that means I'm down 85 meters. And so I can put in for my displacement at the end there, I can just put in a negative 85 meters. So negative 85 meters there, that's my net displacement. If I'm putting that in with a negative, I should be able to solve then for my time. Now, we have one equation that has all of these variables, but it'll end up being quadratic. So in this case, we will have to solve for our final velocity first. And once we know our final velocity, then our time will be easy to solve for. To solve my velocity, then I have my Vf squared equals Vi squared plus 2a and d. My Vf squared then, which is what we're looking for, will be equal then to the square root, basically of these terms here. So my Vi is that 120 sine 25, and don't forget to square that, plus 2. Now watch your signs really carefully here. Negative 9.81 and negative 85. Now if you forget the negative, and most commonly it's done in the 85, you'll actually end up subtracting this term. If you're negative with both of them, you end up adding it. And so it makes a big difference to your final answer. So those two signs, make sure you're watching those really, really carefully in these questions. It's an easy place to make mistakes. So this one here is going to be plus or minus 65.1 meters per second. Now remember for these ones here, when you're solving for VF or VI in this equation, you get the plus and minus. And so you have to decide what that's going to be. Now again, that's not too difficult in this case because we know it's heading downwards. And so that VI has to be in the negative direction. And so the VF that we're going to be looking for is actually going to be negative 65.1. But just remember from that equation, you always have to get the direction from the context. Now that I know my VF, then my my time is easy to find. So my acceleration equals VF minus VI over t. And so t is just equal to then VF minus VI over a. So I can put my values in for that over here. So time is equal to a VF then of negative 65.1 meters per second. I'm subtracting then that 120 sine 25 You can put a value in for that, of course, as well. And I'm dividing by negative 9.81. And so in this case, then my time is going to end up being then 11.8 seconds. And that'll be the time, of course, in both components. But we'll find it using then that y component. The next one then, how far does the cannonball travel horizontally? So now we're going to our horizontal component, and so that's looking for this value over here. Now I know the initial velocity is going to be just the horizontal velocity, so it's going to be the 120 cosine then the 25-degree angle. I'm looking for the distance, and the time in the air is going to be the same as it was for the y component, which is what I solved for in B. So for part C here, I'm just going to be looking for that or x component. And so in my x component, I know then for my velocity, that's going to be the 120 and then times cosine of the 25. And that'll be the constant velocity all the way through. Distance, of course, is what I'm looking for. And then my time is going to be that 11.8 seconds from the part B there. And remember to hold that number all the way through in your calculator. This one's going to be pretty short. D equals V times T. And so my distance in this case then will be that 120 times cosine of 25, and then all times the 11.8 seconds. Now do pull all those numbers through in your calculator when you're doing that, but that'll give us 1,284 meters. We want to get to 3 significant digits, so around to 1.28 kilometers then away from the base of the cliff. Now the last thing we're going to be doing then is solving for the velocity of the cannonball when it hits the ground. And what you need to recognize for this is it's coming down at an angle here, and so I do have the two components. Now I've solved for both of those components already. So in part B I solved for my VF as being 65.1, and then for this one here I know that I have this constant velocity in the x component at 120 cos 25. So I don't actually need to solve anything new here. I can just put those vectors together into the triangle. And so my velocity vector heading downwards like this, we'll have then those two components. I'll get the y component and then the x component. And so I can fill those two in. This is the 65.1 meters per second. And then this is just going to be that 120 cos 25, which works out to about 108.7 meters per second. And that one there is just coming from 120 cos 25, which we have then from our x component over here. Now to solve for the velocity, we're just going to do Pythagoras' theorem. So this is going to be my v net, or my final velocity. And so that v net squared is going to be equal to that 65.1 squared, and then plus the 108.7 squared. So my v net, when I take the square root of that, my v net then is going to solve to 127 meters per second. Now I was looking for a velocity, so we should also find then the angle, and we'll look at the angle relative to the horizontal. And so when we're looking at this one over here, we're going to be looking for this angle over here. Now this angle is going to be equal to this angle. So this is the actual angle we're looking for, because that's the base of the vector, but that'll be equal and opposite to this one here. And this one's inside the triangle, so we'll just solve for that one there. And we can use tan, of course, to find that. And so my angle from the horizontal will be tan of theta equals the 65.1 divided by the 108.7. My angle then will be the inverse tan of that fraction, so the 65.1 over the 108.7. And so my angle, when I solve for that to 3 significant digits, will be 30.9 degrees, and that's from the horizontal.